Today we are diving deep into hidden wear mechanism of blast furnace hearth through the lens of post-mortem analysis. This method doesn't just study failure; it unlocks a roadmap for resilience and longer campaign life in steelmaking. So let's begin our forensic tour of one of the most critical zones in iron making. At the core of every blast furnace lies the hearth lined with high performance carbon or graphite blocks. Operating continuously at temperature above 1500, this zone is constantly exposed to molten iron, slag, alkalis, and CO gas. Its integrity defines the furnace productivity, safety, and cost efficiency. When failure occurs, understanding how and why becomes very essential. Now question arises that why postmortem analysis? Postmortem analysis is akin to an industrial autopsy. It deciphers complex real world degradation pattern often missed by simulations. By examining a wound hearth, engineers gain a critical insight into wear mechanisms, refractory behavior, and failure zones. This data drives improvements in design material and repair strategy, shifting our approach from reactive to predictive. In this case study, CSN blast furnace number 2 underwent a partial repair in 2009, triggering post-mortem evaluation. The furnace had an intense production rate of 2.4 ton per cubic meter per day. Graphite blocks were used in three zones of focus: the taffle, the intermediate zone, and the area opposite the taffle. Each zone revealed different stories of stress, wear, and infiltration. To assess the inner refractory, engineers used a 100 bore saw to extract cylindrical sample at various elevations, that is, from the bottom, from the middle, and top. Each sample included hot and cold phases to provide a full thermal and chemical profile. Once removed, the drill holes were restored, used carbon mortar to preserve a operational integrity. A suite of characterization techniques was applied: bulk density and porosity via Archimedes method XRF for elemental compositional XRD for phase analysis, ACM EDS for microstructural insights. These allowed a layered understanding from surface infiltration to atomic scale corrosion, which are essential for mapping damage gradients. Zone 1 opposite of taffle, zone 1 reveal the least damage. Bulk properties match those of new refractory blocks. No major chemical infiltration or phase changes were detected. This suggests how exposure to aggressive agent, reaffirming that mechanical wear alone doesn't dictate degradation. It's the synergy of chemistry, temperature, and turbulence. Intermediate zone or zone 2. This zone marked the onset of chemical attack. Sulfur vapor had infiltrated and crystallized into rhombohedral forms at around 450 degree centigrade. These deposits disrupted graphite flake bonding, making the material more porous and susceptible to slag and metal penetration, a silent degradation mechanism that precedes visual failure. Zone 3 and Tafel area. This zone faced extreme damage. Only 7% of the original thickness remained. Infiltration by zinc, phosphorus, slag, and molten metal was widespread. The damage was worsened by turbulent flow during tapping. We observed carbon dissolution, shrinkages, and a spike in porosity. This zone exemplifies the harsh reality of operational wear under peak thermal and chemical stress. Now, coming to key degradation mechanism, the wear mechanism were multifaceted. The carbon corrosion, alkali and zinc vapor attack, sulfur infiltration, slag metal penetration. These were influenced by impurity levels in raw materials and operating conditions. Knowing the enemy allow us to engineer better defenses starting with refractory composition and furnace geometry. To wrap up, Tafel Jones damaged regular inspection. It also demands a regular monitoring and recording of the data and targeted design enforcement too. Raw material quality directly affect refractory longevity. Zinc and sulfur are silent destroyer that bypass thermal defenses. Postmortem analysis is not just forensic, it's strategic. Let us refine future campaigns, enhance safety, and reduce cost through a smart